I hope you're fine and doing well. Yes, good morning, Adrian. Good morning, Donna. You can use your speakers. You can use your microphones, okay? I'm not able to see the chat. Okay, so that's today's topic. Sequence and series are very straightforward, and I'm sure we are not going to have a difficult time while trying to explain the concepts, okay? So this area of mathematics is quite of help when it comes to analysis of mathematical problems that require a certain period of time to compute. Like, for instance, you talk about the loans in the banks, okay? Talk about the loans. You talk about issues of insurance premiums and so on and so forth, okay? So they require a certain period. The insurance guy will call it the maturity period, okay? So the main aim of this particular topic for computer scientists or software engineers is basically to get that concept so that in case or in a way you are designing a project for maybe the insurance solutions or the banking sector, specifically for issues to do with loans, mortgages, and so on, then you have that foundation. You have that foundation, okay? So we say that a sequence is basically a set of quantities that are arranged in a definite order. We'll have definite and indefinite to mean synonymous to countable and uncountable. Okay. So a sequence can also be said to be an ordered list of numbers. This definition is quite often referred to because in mathematics we do a lot with numbers, okay? But the first definition that is talking about quantities is also very powerful and universal because a set can be of any other thing apart from numbers, okay? But in mathematics, we do a lot of numbers. So the second definition would fit our situation. Then what is a series? It refers to the sum of the terms in a sequence. Now, what are these terms? These now are the individual entries. The individual entries representing a given sequence, either in form of numbers or in form of variable elements or in form of quantities, they are what we call the terms. Okay, so they're the individual entries. So in mathematics, we have types of sequences. We have types of sequences that will do two different things, or provide solutions to two different set of problems. So we have arithmetic, okay, progression, and we have geometric progression. So what is the difference between these two types of organizations? What is the difference between these two types of organization? For AP, or arithmetic progression, there's a difference between the terms. There's a difference between the terms, and we call them successive terms, terms that follow one another. Okay. If the progression or the sequence, if the progression or the sequence has a common ratio, okay, not difference. Okay, so here we're talking about the difference. But if the common, the number that is separating one term from the other is not a difference, then it should be a ratio. Okay, so difference is the normal mathematics that we all know about. Okay, so for instance, if you look at the sequence presented here, this sequence here, you can determine the difference. If you look at it, there's definitely no ratio there. Definitely there's no ratio there. Because you look at 5 moving to 7 to 9 to 11 to 13 and to 15, then you realize there's no ratio there. Ratio is either division or multiplication. Difference here, the term is used to mean an addition or subtraction. So it doesn't have to be addition. It doesn't have to be a subtraction. Maybe the way the word always is deemed to mean. It's either an addition or a multiplication or a subtraction. So we're saying the common difference for that arithmetic progression is 2. 2 provides the difference between the terms in that particular sequence or progression. So we say, in general, our terms of an AP or an AS can be generalized as shown here. Can be generalized as shown here. Okay, so that's the general form of how the terms in an AP or an AS are expected to move. So example 1, 4, 7, 10, 13, 16. So you'll have to obtain the difference. You know what D is, you know what A is. So you obtain the difference from those successive elements or terms in that sequence. So example 2, the same thing. Example 3, the same thing. So you don't need to struggle with that. It's basically going to get the difference. Is it an addition or is it a subtraction? So mathematically, our formula or our discussion can be summarized with this. So that if I know the initial term of an arithmetic progression, and I know the common difference, D, then I can be able to obtain any of the term in that sequence. Even if it's a term that if we do counting, we'll reach there next year, then I can still be able to compute that using that generalized mathematical formula. So M refers to, of course, the total items or the total terms in that sequence, the total terms in that sequence. So if you need any term for an AP, that's the model or that's the mathematical path that you need to take. So that is what I've just explained in the previous slide. So that's how you can apply that formula there. So you're told find the 10th term of the sequence, and the sequence is given below there, 3, 5, 7, 9. So you need to plug in everything in your formula. Look for your D, look for your N, and of course look for your A1, which is the first term. When you plug them on to that particular formula, you're supposed to arrive at 2, 1 as the 10th term of that particular sequence. What you just need to note, very simple, is that if the total number of terms in a sequence is not mentioned, then the term that is being asked for, you assume that should be the last term of that sequence. So if you're told to get the 99th term of this series, okay, you're supposed to get the 99th term of this series, then you assume this series is going to have 99 items, and then you use that to compute your term that is being required. But you can be told the total number of terms at the same time you asked for a specific term. So you remember that that is not the last term, but the last term is the one that has been mentioned. So you get the difference. So example 2 is a similar approach, just presenting the same thing. The only difference there is that we are not adding, but we are doing, we are adding, but we are adding to negative numbers, okay? So those are, Okay, so if we know how to get the terms in a sequence or in a series, then the other important thing is to know how to get the totals of those particular terms. Okay. So we can compute the total of terms in an arithmetic sequence. We can compute the total terms in arithmetic sequence. Generally, the addition in mathematics will follow this order. Okay. The addition in mathematics will follow that order. It's just the normal addition of adding everything, adding 1 plus 2 plus 3 plus 4 plus 5, and till you get to the last item. But now that is not going to be possible because we are talking about strings of numbers in this particular sequence. You're about thousands and thousands of numbers. You want to calculate the premium or the amount to be paid at the end of an insurance cover for 10 years with so much changes in between, okay, additions and subtractions in between. So you can't be able to do that. So that's when now we pick the general formula for computing the totals. But mathematically, we should follow this particular procedure. Mathematically, we should follow this particular procedure. Now, so you don't need to really get worried on how the formula is derived. It's not really a big issue, but you can try and have a look at that process that I've just provided for you there. But now, generally, our formula for obtaining sum should be this. So this should be Sn, okay? Sn, n is a subscript, sum of n numbers, okay? Sn should be a subscript. But it was mistyped there, okay? But now this is the formula. So we know what n is, we know what a is, and we know what d is. So we don't need to really go back into that, okay? So if you want to obtain your total sum or totals of items or terms in arithmetic progression, then that is the way to go. That's the way to go. So an example is provided for there. Find the sum. So our sequence is 2, 4, 6, 8. Our n is 12. We have a total of 12 numbers there. So we plug in our numbers here, just the same way the formula was showing here. Look at this. Any question so far? Any question? Swali? If you don't have a question, then give me an answer to this. Give me an answer to that question. So find the sum of the first 7 terms of the series. Yes? Great. So the sum of the numbers there is 70. Is this correct? Is that correct? Let's look at the other version of sequencing, the other version of sequencing, which is geometric progression. And I had mentioned that if the other one was a difference, minus or plus, then geometric is going to be multiplication or division. It's going to be multiplication or division. And that's what we're going to call the common ratio. That's what we're going to refer to as the common ratio. So while the other one was D, this is going to be R, common ratio. Okay? This is going to be R for common ratio. And of course, it has to be some constant value. Okay? If you're multiplying by 3 or we're multiplying by a third, there has to be some consistency in that particular process. Okay. So let's look at example 2, 6, 18, 54. 2, 6, 18, 54. The ratio there probably is a multiplication. Okay. So 6 going to 18, 18 to 54 is a multiplication by 3. Okay. Look at the other one, 10, 5, 2.51.25. Of course, when the sequence is reducing from left to right, or from the first term moving to towards the last or the other subsequent terms, then definitely the ratio is a division because we are reducing, we are going down. Okay, so this one is multiplication by half or 0.5. Okay, or rather division by 2, if you love to say that. So in other words, our R is 3 and 0.5 respectively for those two examples that are provided there. So we can even have ratios that involves logs, okay, or that involves powers. Okay, so you can have such kind of ratios like this one which is being given here, where the common ratio is moving. Okay, so we are saying in general, our terms in a GP or in a GS, we can compute it in this order. We can compute that in that particular order. And we're saying R must not be equal to 0 because otherwise our terms will remain at 0, will not be moving because we are multiplying by R. So just the same way we've looked at the arithmetic sequencing is the same way this will span out. So in general, this is our formula where A is the first term, just the same way it was the other time. And of course, R is the ratio or the common ratio. It's common in the manner in which it appears because it's applicable to all the numbers or the terms within that particular sequence. So you be very careful when you are coming up with your ratio so that if it is a division, you don't miss. If it is a multiplication, also you come up with the right value. So multiplying by half is similar to a division by 2. Okay. So you can look at this example here. We've got our R at 2, -2, just because of how the processes move. So you'll determine. Okay. So look at this, a bit interesting, because -11 by -2 is 22. 22 by -2 is -44. Okay, so there's that alternation of the sign also. There's also that alternation of the sign. So if this is the case, we have 4, 8 over 3, 16 over 9, 32 over 27, 64 over 81. So coming up with the ratio here sometimes is a bit tricky. Okay, but now pick the previous, the subsequent number and divide by the previous term, then you can be able to arrive at that. Okay. Okay, so that's how you compute your ratios. That's how you compute your ratios, especially where the ratio cannot be seen with a lot of ease. So 8 over 3 divided by 4 is like 8 over 3 multiplied by a quarter. Then you obtain your 2 over 3. So in general, to find our term, that's how we go about it. Any term in a GM, or not a GM, but in a geometric progression or a geometric sequence, then that's how we approach it. Yeah, that's how we approach it. How about the sum? How about the sum? So these are just examples of how we approach the sequencing there. So 2, 6, 18, 5, 4. Okay, so those are just examples on how we determine the terms there. So those are more examples. I've posted the notes already. You can have a look at them at your own time, just to familiarize yourself more if you have issues with the computation of subsequent terms. Now, so we have to get the terms. This is our formula. Get the term, that is our formula. So this is only valid. Remember, that is only valid if R is less than 1. Okay, so that formula is only valid if R is less than 1. Meaning, what we are trying to avoid is that we don't need a negative value or possibly a division by 0. Okay, if R is not greater than 1. If R is not less than 1, rather. Okay, we are avoiding a scenario where we can possibly have 1 here. So 1 minus 1 is going to be 0. And that means we're going to have a 0 as the denominator, which is going to kill everything. So if r is less than 1, then that formula stands. If r is greater than 1, then you need to reverse it. Okay, just reverse the position of n. Okay, so let n be here, n raised to power r, not n, r raised to power n, and of course this one will be r minus 1. So that is in a scenario where your r is greater than 1. A scenario where your r is greater than 1, so that you avoid division by 0, or rather division by a negative value. If you're calculating the sum and then you get total which is negative, really that doesn't make sense. Okay, so you need to always keep that in mind, that the value of r when using this formula will also determine how your formula look like. You just need to reverse the values of 1 and r, the positions rather, and then you're still good to go. So in geometric, this is the formula we use for computing sums or computing totals of a progression. Maybe examples, an example to roll up that. So that's how you get this. So that's how you obtain that process. So we have number 2 there, that is beta. So we have in a sequence of 3, the third term, not in a sequence of 3. The third term is 3 and the sixth term is 9. And you are required to get the first term, okay? So you just need to equate the two equations, and then you'll have your two equations and be able to solve out. So if you know A1 and you know A4, you know A3, not the third term and the sixth term, okay? So you know those two, then you can create two equations, okay? One for the first, for the third term, and then the other one for the sixth term, and then you will solve to obtain A from there. You will solve to obtain A from there. So the approach here is slightly out of context. The approach there is slightly out of context. It's not complete. Because we are looking for A, okay? We are looking for A. So what do you get from here? The first term in this sequence. So you can pick these examples. Just to beef up what we've discussed, you can pick up these very wonderful examples. So you can pick on example 10 and pick on example 11. Okay, just to demonstrate how these progression work in a better way. Okay, let's demonstrate how the progression work in a better way. So if 3, 6, 12 are the numbers, then that's how you can obtain the 10th term of that sequence. And then problem 11 is talking about getting the sum. With very good fractions there to just challenge the process of obtaining the common ratio. So you can pick them as part of your examples in your notes. So confirm, you can see the marks that I'm trying to make on the document just to show so that our communication is a little bit better. Okay. So our ratio is 3. I told you how you get your common ratio in a case where you have fractions that are a bit difficult to use. Then because R is greater than 1, you need to reverse your equation or reverse your formula and obtain that. So if you substitute your values properly, then you'll be able to get about the same figure there for 546 as the total sum of the 7 terms of that particular series. Okay, so that's how that example should be sorted out. You just need to reorganize your indices well. Just remember your indices, and then you're good to go. Okay, yeah. So any question as far as that representation of indices and not indices per se, but sequence is concerned? Any question? Any question? Yeah, it's an online learning. Therefore, participation is very important so that I know whether you've understood or not, what we need to adjust. Okay. So it's very important that you continuously engage. Otherwise, I might be teaching people who just joined and dropped their phones there or laptops there and went on their businesses. Okay, so I love to continuously engage you so that I know the class is active and the members are present. Otherwise, if you're quiet, I might assume that you are not even no longer part of the class. Okay, that's aside. I'm going to post application questions on series and sequencing on the portal. Okay, on the portal. So once I post them on the portal there, you can have a look at them, do them and post your answer. Okay, do them and post your answer so that you can compare what each and every person is getting. Otherwise, I'll summarize the topic at that point. I'll summarize the topic at that point. The notes are posted already on the platform, and I'll post more examples, not example, but questions, forms. Then we can, you can be able to try and work them out and let me know. Otherwise, I think we'll summarize today's class at that point. Thank you guys for coming and stay safe and keep on reading. If there's any concern, kindly always get in touch. Remember, this is a remote learning, so we really don't meet physically, and therefore it's only through communication that we can be able to move forward. Yeah, thank you and have a lovely week ahead.
You are currently the only person in this conference.